All right, let's talk about the magic that makes all our modern software actually work. We're going to go on a journey from, really simple step-by-step instructions to this incredible world of interacting digital objects. This is the invisible blueprint behind pretty much every app and website you use every single day.
So here's the big question, right? How do you build something enormous, like a modern app, with millions of lines of code, without it just collapsing into total chaos? Seriously, how do you keep it organized, secure, and manageable? How do you stop it from turning into this tangled nightmare that nobody can fix or update? Well, the answer lies in this one brilliant idea that completely changed the game.
Okay, but before we jump into that amazing solution, we kind of have to go back in time and understand the old way of doing things. It all starts with the most basic approach to writing code, which is basically thinking of it like a recipe.
You see, at the heart of any computer program, you've got something called an algorithm. And honestly, the best way to think about it is exactly like a recipe from a cookbook. It's just a super clear, step-by-step list of instructions that tells a computer what to do to get something done.
So this whole recipe way of thinking, that's called procedural programming. You just write a list of commands, and the computer runs through them from top to bottom, one after another. And look, for a simple job like baking a digital cake, it works great. Get ingredients, mix them up, add some stuff, bake it. Easy.
But what happens when you're not just baking a simple cake anymore? What if you're trying to build, an entire city? All of a sudden, that single super long list of instructions, that becomes a massive problem.
And that is exactly what started happening. As software got way more complicated, this whole procedural approach just started to fall apart. The code turned into this tangled mess that was almost impossible to maintain. You'd make one tiny change over here, and it would cause some totally bizarre error way over there. And even worse, the data, the really important information the program uses, it was just out in the open. Any part of the program could accidentally mess with it, which, as you can imagine, was a huge security nightmare.
So you can really see the two different ways of thinking here. On one hand, you have the old procedural way, a top-down list of instructions working with data that's just kind of floating around, totally insecure. But then this new idea started bubbling up, a bottom-up approach. The focus shifted to creating these secure, self-contained objects that can actually act like things in the real world. And let me tell you, this was a revolutionary shift in thinking.
And this new way of thinking, it got a name: Object-Oriented Programming, or OOP for short. The big idea was, instead of one giant recipe, you could now build software out of a whole world of these little interacting objects. It was finally the answer to that crisis of complexity.
So, what was the big idea here? Well, the core concept of OOP is actually pretty simple and elegant. Instead of writing one massive long list of instructions, the question became, what if you could build your program out of smaller, reusable, self-contained little components? Think of it like building with Legos instead of trying to carve something out of a single giant block of wood. And those Lego bricks, we call them objects.
Okay, so to make these objects, you first need some kind of plan, right? In OOP, we call that plan a class. A class is literally the blueprint. It doesn't do anything by itself, it's just a design. It defines what properties something has and what it can do. So, for instance, you could have a car class. That blueprint would say that all cars have a color, and they can all be driven.
So if the class is the blueprint, then the object is the real thing you build from that blueprint. It's an actual instance of the class. So using our one car blueprint, we can create tons of different car objects. A red Ferrari object, a blue Honda object. Each one is unique with its own details, but they all share the same basic abilities that were laid out in the original blueprint.
Okay, so how does this all actually work in the real world? Well, this whole object-oriented world is held together by a few really powerful core principles. Think of them as the superpowers that give it all its strength and flexibility.
First up, we have encapsulation. This is a huge one. It's the idea of wrapping up an object's data and the code that works on that data all together in a single unit, like a protective little capsule. What this does is it stops other parts of the program from just reaching in and messing with the data directly. And that, right there, makes everything way more secure and stable.
Next, we've got inheritance. This is all about not having to reinvent the wheel.
It lets you create a new class that's basically a more specialized version of one you already have. So for example, a sports car class can inherit everything from the basic car class, but then you can add new special stuff to it, like a turbocharger. It means you get to reuse code, and it saves an incredible amount of work.
And finally, we have polymorphism. Now that's a fancy word that just means many forms. And the idea is really simple. A single action or command can behave differently depending on the object it's being used on. For example, you could have one draw command. If you tell a circle object to draw, it draws a circle. If you tell a square object to draw, it draws a square. Same command, different results. It's what makes the code super flexible.
Now, these are all really powerful ideas, right? But they were kind of just concepts floating around. They needed a programming language that could take these ideas and bring them to everybody. And in the mid-90s, that language finally showed up.
It all kicked off in 1991 as a thing called Project Green, meant to make software for TVs and stuff. By 95, it got a new name, Java. And when the first real version was released to the public in 1996, well, the timing couldn't have been more perfect. It landed right at the beginning of the World Wide Web explosion, and it just took the entire development world by storm.
So why did Java get so huge? Well, it came down to a few things. First, it was built from the ground up on these object-oriented principles we've been talking about. It was also designed to be really secure, which was perfect for the internet. But the real killer feature, it was platform independent. Their whole motto was, write once, run anywhere. That meant you could write a Java program and it would just run on Windows, on a Mac, on anything, without having to rewrite it. That combination was a game changer. It powered all those huge business applications and, later on, became the backbone of Android, literally putting a supercomputer in billions of pockets around the world.
And here's one of the biggest reasons developers absolutely loved it. See, in older languages like C++, programmers had to manage the computer's memory by hand. It was a total pain and it was super easy to make mistakes. But Java, it just handled all of that for you automatically. That one change, as simple as it sounds, made programming so much faster, easier, and way more reliable for millions of people.
There's a famous saying that really sums it all up. In Java, everything is an object. And that's the key. Java wasn't just a language that had some OOP features bolted on. No, it was a language where thinking in an object-oriented way was the only way. You literally couldn't write a program without thinking in terms of classes and objects. And that forced an entire generation of developers to really embrace this powerful new way of building software.
So this incredible world of objects that we've been walking through, it's what gave us the incredibly complex software we all depend on today. But here's a thought. This was an idea that was born back in the 90s. That's over 30 years ago. It really makes you wonder, right? As our digital world gets even more complicated, what's going to be the next big idea? What's the next revolution that's going to change everything all over again?